Welcome to today's paper reading. Today's paper is titled, Improving Retrieval-Augmented Language Model with Self-Reasoning. This paper was published on the AR14 preprint by Yuan and colleagues from Baidu Incorporated, China. The research aims to solve problem X by investigating Y. The research focuses on Z and its impact on A. Understanding problem X is essential to advancing the field of Y. Previous research has shown B, highlighting the need for further investigation of Z. The Retrieval-Augmented Language Model, RALM, enhances large language models, LLMs, by incorporating external knowledge during inference, which helps to mitigate factual hallucinations. However, RALMs face challenges such as reliability concerns due to noisy retrieval and traceability issues due to lack of proper citations. To address these, the authors propose a novel self-reasoning framework that includes three processes: relevance-aware process, RAP, evidence-aware selective process, EAP, and trajectory analysis process, TAP. This framework has been evaluated on 4 public datasets, demonstrating superior performance with only 2,000 training samples. Figure 1 illustrates the self-reasoning framework's process of generating reasoning trajectories. It involves 3 key processes: a relevance-aware process that identifies documents relevant to the question, an evidence-aware selective process that chooses pertinent information from these documents, and a trajectory analysis process that synthesizes this information to form a coherent answer. This framework aims to enhance the reliability and traceability of retrieval-augmented language models, RALMs, by leveraging the reasoning capabilities of large language models, LLMs. In the field of retrieval-augmented language models, RALMs, several studies have explored enhancing the performance of large language models, LLMs, by incorporating externally retrieved information. For instance, Isicard et al., 2022, Gu et al., 2020, and Borgot et al., 2022, have investigated this approach. Some works, such as those by Menick et al., 2022, and Nakano et al., 2021, focus on instructing or training LLMs to answer questions using retrieved documents while providing citations. Gao et al., 2023b, proposed an end-to-end system for retrieving supporting evidence and generating answers with citations, without updating model weights. Other works, like those by Schick et al., 2023, Yao et al., 2023, and Jiang et al., 2023, instruct or fine-tune LLMs to use external tools for dynamic retrieval, offering an adaptive method for when and what to search. Additionally, Gao et al., 2023a, improved the attribution and factuality of language models through a post-process retrieve and edit approach. Figure 2 illustrates the self-reasoning framework designed to enhance retrieval-augmented language models, RALMs. At the top, basic language models, LLMs, answer questions using their inherent knowledge. In the middle, standard RALMs utilize retrieved documents to assist in answering questions. At the bottom, our self-reasoning framework employs self-generated reasoning trajectories to produce answers. This framework aims to improve the robustness and accuracy of RALMs by leveraging the LLM's own reasoning processes. In the preliminary section, the authors discuss various existing methods for improving the robustness of retrieval-augmented language models, RALMs. These include using natural language inference models to filter irrelevant documents, employing memorization models to compress retrieved documents, and generating summaries of documents as notes. Unlike these methods, the authors propose an end-to-end framework that identifies key sentences and cites relevant documents without relying on external inference models. They also define the problem of retrieval-augmented generation with self-reasoning, where given a query and a corpus of documents, an LLM generates an answer that includes reasoning trajectories. This approach aims to enhance the performance of LLMs more efficiently and scalably. The method section of this paper introduces a novel framework for self-reasoning, which is composed of 3 main processes: the relevance-aware process, the evidence-aware selective process, and the trajectory analysis process. These processes are designed to enhance the reasoning capabilities of large language models. Additionally, the paper details the process of data generation, where GPT-4 is utilized to generate ground truth labels and create training samples. Quality control methods are employed to ensure the accuracy of these samples. Finally, the model training section describes the use of a standard language modeling objective and a stage-wise masking strategy to train the model effectively. The experiments were conducted on 4 datasets: natural question, NQ, PopQA, ASQA, and Fever. Different retrieval methods were used for each dataset, such as DPR for NQ and Contriever for PopQA. The evaluation metrics varied depending on the task type, with accuracy used for short-form QA, EM recall and citation metrics for long-form QA, and accuracy for fact verification. The main results show that the self-reasoning framework significantly outperforms baseline models, especially in efficiency, requiring only 2,000 self-reasoning trajectory samples compared to 46,000 for self-RAG. Additionally, self-reasoning achieved higher accuracy in fact verification tasks. Table 1 presents a comprehensive comparison of the performance of various baseline models across 2 short-form QA datasets, a long-form QA dataset, and a fact verification dataset. The models evaluated include Llama 27B, Llama 213B, Llama 27B Chat, Llama 213B Chat, Vicuna 7B, Vicuna 13B, Llama 2FT7B, React, Recomp, Self-RAG 7B, Self-RAG 13B, Self-Reasoning 7B, Self-Reasoning 13B, and GPT-4. The results highlight the effectiveness of retrieval-augmented LLMs over basic ones, with self-reasoning frameworks showing superior performance compared to most strong baseline LLMs. Notably, self-reasoning's efficiency in training with fewer samples stands out, contrasting with the resource-intensive training of models like self-RAG. Figure 3 presents the noise robustness experiment results across 3 datasets, NQ, PopQA, and Fever. The experiment compares the performance of 13B parameter size models, specifically self-RAG and Vicuna, against our self-reasoning framework. The results consistently show that our framework outperforms both self-RAG and Vicuna, demonstrating its robustness even in the presence of noisy documents. This highlights the effectiveness of our approach in maintaining high performance under challenging conditions. The ablation study evaluates the contributions of each process within the self-reasoning framework. The removal of the relevant-aware process, RAP, causes performance drops, especially in fact verification tasks. The evidence-aware process, EAP, is crucial for accuracy, with a significant decline when removed. The trajectory analysis process, TAP, also improves performance, particularly in long-form QA. In the retrieval robustness analysis, the order of retrieved documents has minimal impact, but noisy documents significantly affect performance, with self-reasoning showing relative robustness. Citation analysis reveals that human evaluation aligns well with automatic evaluation, often yielding higher scores. Table 2 presents the results of an ablation study conducted on 2 short-form question answering, QA, datasets and a fact verification dataset, all using models with 13B parameters. The origin model, which includes self-generated reasoning trajectories, demonstrates superior performance compared to models without the relevant-aware process, RAP, evidence-aware process, EAP, or trajectory analysis process, TAP. The study highlights the individual contributions of each process to the overall accuracy. Additionally, the effectiveness of gradual learning, GL, and quality control, QC, in data generation is evident, as their removal leads to a decline in performance. This table underscores the importance of each component in the self-reasoning framework for achieving robust and accurate results in QA and fact verification tasks. Figure 4 illustrates the comparison between human citation quality evaluation and automatic citation evaluation on the long-form ASQA dataset. The key observations include the alignment of relative rankings by both human and automatic evaluations, with human evaluation frequently resulting in higher scores. Additionally, a citation precision score of 1 is awarded when the citation fully supports the statement, as determined by human annotators. The study demonstrates that RALMs can significantly enhance the performance of large language models and knowledge-intensive tasks. However, concerns about reliability and traceability remain. To address these issues, the authors propose a novel self-reasoning framework. This framework aims to improve our RALM performance by utilizing reasoning trajectories generated by the LLM itself. The framework includes a relevance-aware process, an evidence-aware selective process, and a trajectory analysis process. Extensive experiments were conducted on 4 public datasets, showing that the proposed framework outperforms existing state-of-the-art models. The study primarily concentrates on enhancing the performance of RALMs through a self-reasoning framework in open-domain question answering and fact verification tasks. While the framework has been evaluated on 4 public datasets, it has not been tested in more complex scenarios such as multi-hop reasoning, code generation, and arithmetic reasoning. Future research should address these more challenging tasks. Although the framework aims to reduce factual hallucinations in LLMs and improve robustness, there remains a risk of generating such errors. Further exploration is necessary to fully assess and mitigate these potential risks. Thank you for watching.